You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. This video will look in more detail at the line object. OrcaFlex uses a finite element model for lines, with properties such as mass, weight and buoyancy lumped at nodes which are connected by straight, massless segments. The segments only model the axial and torsional properties of the line. This is known as a lumped mass model. All line nodes have their own local axis system, and the local z-axis represents the axial direction. Because segments cannot bend, it is important to optimize their length in order to create an appropriate representation of the line you are modeling. A good analogy is the use of straight segments to approximate a circle. The greater the number of segments, the more accurate the circle looks. But it is important to remember that the program needs to make calculations for every node in a line, and the greater the number of segments, the greater the number of nodes. There is therefore a trade-off between accuracy, in this case how realistic the circle looks, and efficiency, minimizing the number of calculations the program has to make. On the left, the line has 100 segments, so 101 nodes. On the right, the line has 10 segments and 11 nodes. The line on the left clearly takes a more realistic form, but has many more calculations to make in finding equilibrium when compared with the line on the right. Deciding the most appropriate level of segmentation for a line can be tricky. Too few segments and the line behavior may not accurately represent the system it is modeling. Too many will result in longer simulations and larger file sizes. Sensitivity studies are recommended if the appropriate segment length is in doubt. We'll spend some time now looking at the line data form. There are a number of settings in the top half of the form, then further parameters within the individual pages at the bottom of the form. The first part of the End Connections section tells us what object the line ends are connected to and where that connection is relative to the parent object's local axis system. If the connection is fixed or free, the coordinates are relative to the global axis system. If it is anchored, it is relative to the seabed origin with respect to the global axis directions. The end orientation settings are in the form of 3 separate angles, and we will discuss these shortly. Release at start of stage lets us release a line end connection at a certain point during a simulation. Next are the end connection stiffness settings, and we will come on to these when we talk about the end orientation settings. We have a section of the form dedicated to statics, including the option to exclude the line completely from the static calculation. We'll talk about these settings in a separate video dedicated to the subject of the static calculation. Looking through some of the separate pages on the data form now, firstly the structure page. This is where we specify the length of the line as well as the segment length. You can see here that the line can be split up into multiple sections. When a line is first inserted into a model, it has 1 section. For this simple example, I'll change this to 3. We can use sections to specify different line types along the length of a line, as well as different segment lengths. We can also specify whether or not we want to check for clashing along particular sections of a line. We'll look at sections again as we start to build a worked example. The next page is the feeding page. This is where we can introduce a payout, a positive payout rate, or a haul-in, a negative payout rate, at one or both ends of a line. This can be a constant value, or can vary over the course of a simulation by using a variable data set. In this data set there is an initial acceleration in the build-up stage from 0 to -2 meters per second payout rate. Then, for the remainder of the simulation, there is a constant payout rate of -2 meters per second. When we select the variable data set and run the simulation, looking at the replay, we see the line dynamically reducing in length, or hauling in, at a rate of 2 meters per second. Moving on now to the pre-bend page, this is where we can provide the data to create a line which is not straight in its unstressed state, such as a spool piece or rigid jumper. Pre-bend can be specified by either curvature or bend angle, and uses the ability to split the line into multiple sections, as mentioned before. It can be difficult to visualize a pre-bent line, particularly when working with compound bends in multiple planes, so a view button is provided to preview the unstressed shape of the line. Moving on, and we have a page for something called midline connections. These are additional connection points and can be added to any or all midline nodes. It is possible, for example, to rigidly connect a line to another object, such as a vessel or even the seabed, by adding a midline connection to every node and connecting each midline connection to the other object. Take this vessel, for example, which has a line fixed at both ends to its side, along with all the midline nodes, by way of midline connections. This line provides a means of modelling contact between the vessel and an elastic solid representing a quayside. We have a page called Attachments next, which allows us to model items such as bend restrictors and buoyancy modules attached at discrete points along a line. We will look at this in more detail in a later video as we use them to model a lazy wave profile in our riser model. Moving on to the contents page now, and we will talk about this in more detail in a later video when we explore line types. However, a quick summary for now is as follows. We have three options when it comes to modelling the contents of a line. The first and default option is uniform, which means that the entire line is assumed to be filled with contents of a uniform density. The next option is free flooding, and this results in the line being filled with seawater up to the instantaneous water surface. The final option is something called slug flow, and this allows for spatial and temporal variation of the contents of a line, providing the ability to model contents flowing through a line at a prescribed velocity. We won't go through the other pages in detail, but these allow for things like applied loads, fluid loads, which are used to model things like disturbance and drag and wake effects, and VIV. A later video will focus on the static analysis, and as part of this we will look at the statics convergence page. Finally, note there is a drawing page common to all object data forms, and this allows us to control how certain aspects of the line are drawn, such as the drawing line weight and colour, the ability to visualise the line nodes in the 3D view, and whether or not to draw contact and slug flow. At the top of the line data form we have some other settings, including the ability to change from the default finite element representation to analytic catenary, though this is typically only required in specific circumstances such as quasi-dynamic mooring analysis. We also need to specify here whether or not to include torsion in the calculation. This is off by default, and its effect can typically be considered negligible for long, flexible lines. In applications with short lines, such as offloading hoses, the effects of torsion may be significant, in which case it would need to be turned on here. The torsional properties for the line type must also be specified if this is turned on. We'll consider the effects of including torsion in a moment when we look at line end orientations. Just before that, I want to take a look at our previously created riser model and review the line segmentation. We looked at the touchdown region in an earlier video, and it's clear visually that the line representation in this area isn't realistic. So it would be beneficial to reduce the segment length so that the behaviour is more representative of the real system. Before doing this, I want to talk about a warning that was received when we first ran the simulation. We can see this if we reset it and run dynamics again. The warning tells us that the riser has infringed its Euler limit. This is the theoretical buckling limit, or the load the line can withstand before buckling. Because the line segments cannot bend, there needs to be enough nodes in the line to allow this buckling to occur, and for the deflected shape to be modelled properly. Don't forget that you can find out more details about this warning by clicking on the More Details button. We'll start by doing what the warning suggests, which is to use finer segmentation. Going to the line data form, we will apply a 1 meter segment length for the whole line. Note that the number of segments increases from 20 to 200. Because of this increase, we can expect to see an increase in simulation time, and this is already noticeable as we watch the simulation progress. Now that the simulation has completed, the first thing to note is that there is no longer a warning. This suggests that the segmentation is now sufficient to ensure that we are modelling the line compression adequately. Of course, that doesn't necessarily mean that the line segmentation is now suitable throughout for the system being modelled. Euler buckling is only one of many things that should be considered when building a system model in OrcaFlex. For example, if you are modelling contact of a line passing over an arch or around a sheave, you will need to have suitable segmentation to model the bending radius appropriately. Considering which are the areas of interest in a model will help you to determine where you may need to further optimize the segmentation used. The replay now looks more realistic with the reduced segment length, but we can clearly see there are issues with the design. We're going to come back to this in a later video when we add some buoyancy to improve the line response in the touchdown region. As mentioned before, we can expect an increase in simulation time with an increased number of line segments, but how do we know how long it took to run? Well, if we right-click on the general data form and take a look at the properties report, this shows us that it took 9.7 seconds to run, compared with less than half a second for the original arrangement. So, how can we improve the representation in key areas such as the touchdown while not adversely affecting the calculation time? Well, we can utilise the ability to split the line into sections. This allows us to set a finer segment length only where needed, leaving longer segments and therefore fewer nodes in areas where the line behaviour might be more benign, such as the anchored end on the seabed. In our case, the two areas we want to focus on are the hang-off point on the vessel and the touchdown region, so we will break the line into 4 sections with finer segmentation in the 2 areas mentioned. I have some appropriate section and segment length in mind, and I could add these by increasing the number of sections to 4 and then typing the data in. However, it is possible to copy and paste data from Excel, and I have a pre-prepared list ready which I'll go and copy now. You can see when I paste this that the number of rows is increased automatically. And we now have 4 section lengths of 10, 70, 90 and 30 meters respectively, and these have appropriate segment lengths defined. If we run the simulation again, we can take another look at the calculation time in the general data form properties report. Remember that this is accessed from the pop-up menu on the General Data form in the model browser. We can see that it took 7.7 seconds, which looks like it might be a good compromise between speed of simulation and accuracy of representation. And finally, if we run the replay, it isn't immediately obvious in this view where the segmentation varies along the line. One option is to make the nodes more visible by going to the drawing page of the line data form and increasing the node width. Alternatively, you may find it helpful to turn on the node axes in the Axes and Labels menu, which you can see helps us to see the node positions and how they vary along the length of the line. We're going to talk about line end connections now. We've already seen the part of the line data form that allows us to connect a line to another object. Remember, we connected our riser to a vessel at one end and anchored it to the seabed at the other. We'll now look at two other sets of data related to end connections: end orientation and end connection stiffness. We'll do this with a simple example to help illustrate it. The design intent for this simple example is to set the line ends such that when statics is run, they are fixed in the horizontal plane as shown here. In fact, what happens with the default settings is that the line solves in a catenary shape with the ends not being fixed horizontally as intended. If we take a look at the line data form, we find out that this is due to the end connection stiffness being at the default value of 0. This is equivalent to the ends being pinned. If we change this value to infinity, this ensures the ends will be treated as being fixed. Let's run statics again and see how the behaviour has changed. OK, that's definitely not following the design intent. We can see the line has taken on an unusual S-shape, but why is that? Turning on visibility of the local axes allows us to review the line end orientation with respect to the design intent. The axes visibility can be toggled in the View menu, the 3D View pop-up menu, or with the shortcut Ctrl+Y. Now that we have the local axes on, we can see that the end orientations are acting such that the local z-axes, EZ, are pointing into the line at end A and out of the line at end B. This is known as the no moment direction. So, it is necessary for us to adjust the orientation of these local axes to match the design intent. For this case, we want EZ to be pointing to the right at both ends, and we'll take a look at how to do that next. In order to set the line end orientation, we need to adjust three angle values on the line data form: azimuth, declination and gamma. These can be visualized using the analogy of a tank turret. Firstly, consider the declination, which can be likened to the vertical angular adjustment of a tank gun barrel. This can be a value between 0 and 180 degrees. We'll talk more about that limitation later. As the value is changed, the orientation of the local axes in the 3D view updates, and this is a good way of checking that you are adjusting the right value. Note that we receive a warning message if we try to input a value beyond 180 degrees. If you need a declination beyond this range, adjust the azimuth first by 180 degrees. Adjustment of the azimuth can be likened to the horizontal angular adjustment of a tank turret, and should be in the range of -360 degrees to +360 degrees. You can see the horizontal angle changing as I progressively adjust the azimuth value for end A of this line. Obviously, +360 degrees and -360 degrees will place the local axes in the same orientation as 0 degrees. Finally, the gamma angle can be likened to the rotation of the gun barrel around its own axis, i.e., rotation of the end coordinate system around its z-axis. As with the azimuth, the gamma angle can be in the range of -360 degrees to +360 degrees, and the gamma angle is only relevant if torsion is enabled on the line. Returning to our simple example, and as mentioned before, we need both z-axes to be pointing to the right, so we simply need to adjust the declination to 90 degrees at both ends in order to match the design intent. Now, when we run statics, we see the end result matches the design intent, a successful outcome. I would encourage you now to pause this video and have a go yourself at recreating that simple example with horizontal end connections. As a final exercise, we will make a further change to our previously built riser model by adding a 5-degree hang-off angle based on the sketch on the screen. If you feel confident enough to have a go, you can pause the video and do this now. Alternatively, I will walk through the process next. First of all, once the model is in the reset state, we need to adjust the orientation of the appropriate end of the line, in this case end A. We know that the direction of the z-axis at end A needs to be pointing into the line, which means for a 5-degree hang-off this will be 5 degrees from vertically down, so the declination needs to be 175 degrees, since 0 degrees is vertically upwards. Secondly, we need to build the end in, which means applying an infinity end connection stiffness. We simply set the x bending stiffness to infinity, and the tilde symbol for y bending means it will use the same value as x. Now, if we run dynamics, we should see that end A of the line is now constrained to a 5-degree angle. If we zoom in to try and look at this, you can see when we run the replay that the motion of the vessel means the line end keeps disappearing out of the view. This is a good example of when it can be useful to change the relative to option in the view parameters. If we set this to the vessel instead of global, the view now stays with the vessel, and it's easier to see the revised behaviour of the line. Of course, if you zoom out, you might start to suffer from motion sickness because the sea and the seabed are now moving, so use this option with care. Okay, we'll come back to this model in later videos to make further changes, so make sure you save your progress so far. In the next video, we'll talk in some detail about the dynamic analysis.